One for high school students and one for general public, and now it's a more technical colloquium, but still I think colloquium, not for general physics and mathematics. Welcome to Thorne.
Thank you, Sasha. Can you hear me in the back?
Yeah.
Okay. So when I was John Wheeler's graduate student in the early 1960s, and when Charlie Misner was his graduate student in the early to mid-1950s, John was pushing the idea that one of the most important things that we could probe in our research is the nonlinear dynamics of curved space-time. What he argued is that general relativity is really interesting in the phenomena that it can predict, but the only things that we knew about were things that were quiescent, things like wormholes, which he was thinking about at the time, what came to be called black holes, and relativistic stars, which people are beginning to think about. But what would happen, for example, when two black holes or wormholes collided and space-time became highly dynamical was a total mystery, and he thought it would be really interesting. And so we tried, and we failed quite badly. But today, much is known about nonlinear dynamics elsewhere in physics. Just to remind you, fluid turbulence, tornadoes, phase transitions in condensed matter, nonlinear optics, for example, all of modern optical technology, colliding solitons, solitary waves in fluids and plasmas, in nonlinear crystals and optical fibers, dynamical behaviors of systems that are quite nonlinear. And what we would like to understand is the analogous highly dynamical behavior of the extremely nonlinear space-time curvatures described by Einstein's general relativity. So, as I said, we struggled and didn't make much progress. And Johnny Wheeler, as those of us who, after I got my PhD, I called his home. I'll just tell you a little story. I'm old enough, I can tell stories. I called his home and spoke to his very formal wife, Jeanette. And I said, could I speak with Professor Wheeler? And she responded, now, Kip, you had defended your PhD yesterday. Now you may call him Johnny. So John understood that it would be extremely hard to make progress analytically, and so he urged his students to begin to develop techniques for numerical simulations, numerical solutions of Einstein's equations. And the earliest work on this was in the 1950s by Charles Misner and then by Richard Lindquist, two of his students of that era. But it took a long time to bring the numerical simulations to fruition, to develop the techniques of numerical relativity. 4 decades for them to reach fruition near the period around 2000, late 1990s, the 2000s, when you could begin to do interesting things. And then 15 more years until you could really study the fully generic situations. And so it's only since numerical relativity became reasonably mature that we've learned a lot. What I want to describe to you is the progress that was made initially with the early crude analytical techniques, and then as the numerical relativity came online, what we have learned in the more recent years. In particular, I'll talk about geometrodynamics, nonlinear dynamics of curved space-time near singularities, then the nonlinear self-coupling of gravitational waves in what's called critical gravitational collapse, then colliding black holes, which create what I like to call a storm in the geometry of space and time, and then finally the use of gravitational wave observations to test what we see in the simulations of colliding black holes. And my discussion will be avowedly technical and will be aimed at physics graduate students and faculty and mathematicians and those who already know some general relativity. But I'll try to make it so at least a little bit of it's understandable to others, but I can't make a lot of it understandable to others. So let's begin with geometrodynamics near singularities. And this does go back a ways. It goes back all the way to Robert Oppenheimer and his student Hartland Snyder in 1939, when they, trying to understand what would happen if a star died and imploded, they did the idealized problem of a spherical, spatially homogeneous cloud of dust that implodes and forms what we now call a black hole. And they watched it implode analytically to form a singularity at the center, surrounded by a horizon, though they didn't understand the horizon at the time. They didn't understand the singularity, but they saw these phenomena, and they and others struggled then to understand what was being predicted by the calculation. Of course, today we all often talk about hanging my wife above the black hole and having the tidal forces near the singularity squeeze her and stretch her, or an astronaut is what most people use, but Carolee has given me permission to use her. Now, there was a big debate in the period from 1939 into the 1960s whether this was relevant at all. Suppose that you had an implosion that had pressure, so it was realistic. More importantly, that it was highly non-spherical. Then would you still form a singularity? And it was widely thought that you would not, that the matter would come in, it would whirl around due to its angular momentum around the center and fly back out, and you would not get a real singularity. And the pressure then would take over and would help prevent a singularity. It turned out, in fact, that this does not happen. You really do form singularities. But let me explain how we came to understand this. Generic singularities was by Lifshitz and Kalatnikov in Moscow around 1960. And they searched for a generic solution of the Einstein's equations that approaches a singularity. So they just said, let me hypothesize I have a singularity, and then I search for a solution that has the maximum number of arbitrary functions in the initial data that would make it generic. And so they counted up how many arbitrary functions in the initial data would you have to have in order that you had generic initial data, and then could you find generic initial data of that sort, in that sense, that actually formed a singularity. That was a search that failed, and so as a result of that, in the 1962 revised second edition, English edition of the Classical Theory of Fields, the fourth Russian edition, there is a section about the absence of singularities in the general cosmological solution, but that really, I think, just general solution of the Einstein equations. This is the edition of the Classical Theory of Fields from which I learned general relativity. And it was right there, all laid out, the details of why you do not get a generic singularity. 1965, Roger Penrose in London had brought techniques of differential topology into general relativity for the first time, and he used them to show that if you have some sort of an implosion that forms a horizon, so you have a black hole in the sense that there is a horizon, that there were time-like whirl lines that go into this black hole that end. They could not be extended to infinite proper time. But why they ended was totally unclear. But these were beautiful techniques he used, the same techniques that Stephen Hawking then picked up and used to prove, for example, the second law of black hole mechanics, that surface areas of black holes always increase. And so these wonderful new techniques gave us theorems about generic situations with a requirement you had some sort of positive energy condition in order to get this conclusion. Matter gravitates, doesn't anti-gravitate. But it gave us no information at all about the geometrodynamics near the singularity. Only a proof that you fall into a black hole, you die, you cease to exist. Things time like whirl lines end at finite proper time. This caused great consternation in Moscow. Roger published this, and then he talked about it at the General Relativity Conference in London in 1965, to which I know Kalatnikov was there, and I think Lifshitz was also there, but I have forgotten whether he was or not. I was there. It was the first major conference I went to as a young physicist. And so they struggled to figure out, was there something wrong with our analysis, and if so, what? And in 1969, Belinsky, a graduate student of Kalatnikov's, Belinsky and Kalatnikov and Lifshitz found the error in their analysis. They found, in fact, what analytically a generic singularity in this sense, that you had the necessary number of free functions in the initial data for them, the initial data to be generic, and then that led to a singularity. This is a photograph just showing me, taken by Charlie Misner, John Wheeler, Yevgeny Lifshitz, Isaac Kalatnikov, and Vladimir Belinsky, and Kalatnikov's wife and daughter, when we were in Moscow in 1971, just 2 years after this. I was in Moscow then in, I think it was 69, it may have been 1970, when they really firmed these results up. And Lifshitz, who was a close friend of mine, gave me a manuscript and asked me to submit it in his behalf to Physical Review Letters. He did not want to have the delay of 4 months or so to have it go through the Soviet censorship process of that era, because he was afraid somebody else would find the error, and he wanted to for them to be the ones who laid it out and said, here's where our mistake was, and not have somebody else tell the world. And so I smuggled the thing out and submitted it for them to Physical Review Letters. So what was the time? It was an approximate analysis. It was referred to later as BKL for Belinsky, Kalatnikov, and Lifshitz. And the basic issue was the following, that if you have time-like geodesics along which you and I could fall, going up to their generic space-like singularity, it was space-like. As these geodesics near the singularity, they become causally decoupled to the extent that asymptotically the Einstein equations, which are partial differential equations, reduce to ordinary differential equations along these world lines, asymptotically at late times. And the solution of those ordinary differential equations is what is called the Mixmaster singularity. This was a homogeneous version of this singularity found independently by Charlie Misner in the US and by Belinsky and Kalatnikov in Moscow, just shortly before this work. And so let me remind you what the Mixmaster singularity is, but I would add one other remark, that matter has negligible influence on this. This is also true in the presence of matter, unless the matter is so extreme that the pressure is equal to the energy density. And that's otherwise, matter just goes along for a free ride. And so this is a very powerful and general analysis. I remind you the Mixmaster singularity is this. And what this says is that if you and I fall into this singularity side by side, asymptotically we become decoupled, and we each see a Mixmaster behavior, but different Mixmaster behaviors, because we're decoupled. And what this Mixmaster behavior is the following. I think of myself now, falling into the singularity, and I get alternately stretched along one direction, squeezed from the sides, then stretched from the sides, squeezed head to foot. And it's an oscillatory stretching and squeezing. There are principal axes of the stretching and squeezing. And so if I take the principal axes initially to be up, down, east, west, and north, south, then I might, for example, have successive east-west squeezing. Down is squeeze, is up is stretch. Squeeze, squeeze, squeeze by growing amounts. But in the up-down direction, I have stretch, squeeze, stretch, squeeze. In the north-south direction, I have squeeze, stretch, squeeze, stretch. So it just oscillates through cycles. And then there comes a point at the end of what they called an era, when the spatial curvature that is present causes a rotation of the principal axes, and the whole process starts over again through another era. And the entire pattern is governed by a chaotic map, sometimes called a continued fraction map, if my memory is right. So here we saw for the first time geometrodynamics exhibiting chaotic behavior. Chaotic behavior in the nonlinear dynamics of curved space-time already back around 1970. There was enormous skepticism in the West of this analysis because it was an approximate analysis, and people in the West who were demanding higher levels of rigor than Belinsky, Lifshitz, and Kalatnikov were demanding could see ways in which it could go wrong. And so there was a lot of skepticism. This came to be called the BKL conjecture obtained by heuristic arguments. And for several decades, there was this this attitude about this. But it was a challenge then to figure out whether this really was a correct analysis, and that was ultimately resolved through numerical relativity techniques. Beginning in the mid-1990s, a program initiated by Beverly Berger and Vince Moncrief. Beverly, I think, was at the time at Oakland University, and Vince was at Yale, 1994, and then carried out by a variety of people with David Garfinkel at Oakland University being the person who had the biggest impact on the final results. And what they found was that indeed the BKL analysis was giving correct predictions aside from a few things that had been missed. Particularly, there were occasional sharp spikes at the end of one of these cycles that were triggered by spatial inhomogeneity. That is, you did not have as complete a spatial decoupling as BKL had thought they had. Cycle some influence of that spatial inhomogeneity. Recurring sharper and sharper at late times, and then corresponding modification of the chaotic map. But qualitatively, semi-quantitatively, the analysis was correct. And so I think now this is looked back on as having been really the first true insights into geometrodynamics by that approximate analysis by the Russians. A little bit later, there was work by, I guess I haven't written down here the people, so by Werner Israel and Eric Poisson, which initiated this work, showing that there are also generic null singularities. And I like to describe this physically with a diagram that comes from my book, The Science of Interstellar, so I'm bringing in some heuristic descriptions, but this is physically what goes on. So Matthew McConaughey falls into a black hole. This is an embedding diagram. It gets heuristic down at the bottom, the embedding diagram for a Schwarzschild black hole. And it falls to the horizon, and roughly speaking, what happens is that first of all, is that there is a BKL singularity that formed down deep inside the black hole when the black hole was born. So this is just my own wild imagination of how to depict a BKL singularity. But what happens beyond that is, heuristically speaking, again, that time is so screwed up inside of here that everything that falls into the black hole after Matthew McConaughey comes crashing down as seen by him in a shock wave that is very, very thin. So it comes down in a fraction of a second as seen by him, even though it's billions of years on the outside. And this shock wave is what was called by Poisson and Israel the mass inflation singularity. The Riemann tensor associated with the shock wave has a sharp singularity, but its double time integral is finite. And I remind you then, say from the equation of geodesic deviation, the double time integral will be the total stretch of McConaughey and squeeze the McConaughey as he nears the singularity, and that is finite with a stretch along one direction and squeeze along the other two directions. For those who know about Penrose diagrams with the compactification of space-time, time running up and space running outward, our entire universe is down in this region, and then that's the event horizon of the black hole it formed. This is what's called the inner Cauchy, or ingoing Cauchy horizon, the outgoing Cauchy horizon. Cauchy horizons in the mathematical sense. And this singularity is forming along where the ingoing Cauchy horizon used to be, triggered by stuff that falls in from the external universe. And there's a beautiful and detailed mathematical analysis of this, but only with perturbation theory. We don't yet have numerical simulations to show this. A little bit later, in 2012, Donald Roiled at UC Santa Barbara and Amos Ori at the Technion discovered that a similar thing happens in this way, that everything that fell into the black hole in the past, a little bit of it scatters back and similarly forms a shock wave type of singularity coming up toward Matthew McConaughey. So he's trapped in this movie between two singularities, and well, you can go watch the movie and see what happens. Here this shock wave is at the outgoing Cauchy horizon, whereas the ingoing shock singularity is at the ingoing Cauchy horizon. Again, the double time integral of the Riemann tensor along a time-like geodesic is finite, but the Riemann tensor diverges. We really need simulations to verify that this is truly what happens. This has all been figured out with perturbation theory, except for the BKL singularity down at the center, for which we have the numerical simulations. And this, I'm just rather surprised the community has not yet been doing successful simulations of what goes on inside the black. Sort this out and be absolutely sure whether this is right or whether we got it wrong. Let me now turn to my second example of geometrodynamics in imploding waves. This began with work by Matthew Choptuik that's rather well known in 1993, when he began with a scalar wave. Just obeys the standard linear scalar wave equation that interacts with itself non-linearly because the scalar wave has energy, and that energy in the wave is used to feed back into the Einstein equations, where it generates some space-time curvature that the wave then interacts with. So that's the form of the nonlinearity. He began with an arbitrarily shaped wave in terms of waveform, and discovered that whatever may be the shape of the waveform, the ultimate behavior is the same. There's a critical amplitude for the wave. And if the actual amplitude is above that critical amplitude, P star, you form a black hole. The wave energy goes in, and it gravitates so much it makes a black hole. And the mass of the black hole is proportional to the amplitude minus the critical amplitude to a critical exponent, if you're borrowing a phrase from condensed matter physics. And numerically, that power is 0.374. If the amplitude of the wave is less than the critical amplitude, then the wave comes in, there's lots of nonlinear interaction, but it ultimately disperses. And you get a maximum curvature, or minimum radius of curvature, say, which is the square of the Riemann tensor to the -1/4 power, has the same dimensions as the mass of the black hole when I set G and C equal to 1. And that minimum radius of curvature scales as the critical amplitude minus the actual amplitude of the same critical exponent, beta of 0.374. The other interesting thing is when P is equal to P star, you get a discretely self-similar behavior in the sense that the wave goes in, it interacts with itself non-linearly, but independently of what waveform you began with. Asymptotically at late times, you have waves that come out that have a particular waveform that's universal, that's discretely self-similar. It repeats over and over again on shorter and shorter length scales and shorter time scales. And as was actually proved analytically by Demetrius Christodoulou a little bit later, you get a true naked singularity, arbitrarily small naked singularity at the end point of that discretely self-similar pattern of outgoing waves. So it's basically a violation of one version of Roger Penrose's cosmic censorship conjecture. And it was enough to win John Preskill and me a bet against Stephen Hawking. And then we did a new bet that said, can you form naked singularities without fine-tuning the initial conditions? You have to fine-tune, so you have the amplitude precisely, the critical amplitude, in order to produce this. But anyway, so we then knew that from this analysis, a numerical relativity analysis, that in geometrodynamics, as in condensed matter, you get phase transitions. It's a phase transition in the sense of the ultimate behavior is quite different depending on whether the amplitude is bigger or less than the critical value. Near the phase transition, you have this discretely self-similar behavior, and you have this critical behavior, critical exponents that show up, all things that are also characteristic of phase transitions. So this was really satisfying again to begin to see now a second set of nonlinear dynamics of curved space-time, which was really quite interesting and which mirrored what you see in other areas of nonlinear dynamics. But that was a hypothetical scalar wave. What happens if you begin with a gravitational wave that implodes? Originally, this was done with modest accuracy by Abrahams and Evans in 1993, and then Yevgeny Sorkin in 2011 did it with much higher accuracy. In this case, you cannot be spherically symmetric. The original analysis of Cha was a scalar wave, but you can't do it with a gravitational wave. And so you had to pose actually symmetric initial data, not spherically symmetric. So you'd lost one degree of symmetry in the initial data. But in that analysis, they found precisely the same behavior with, to the accuracy of the numerical work, the same critical exponent, the same independence of the actual waveform in the initial data, and moderately strong evidence for discrete self-similarity. So a real universality, not just in what waveform you began with, but what kind of wave you had, massless scalar field, or a massless graviton field, classical general gravitational waves. There's been a lot of further work on such critical collapse with things like the collapse of a cloud of dust and so forth. And with other kinds of material going in, you actually get a little different behavior on other critical exponents. There's still the universality. But as, for example, with the onset of convection, there appear to be a handful of roots that you go a handful of behaviors, not a whole range of behaviors, but it's a small handful of behaviors at the phase transition as you go from p bigger than the critical value to p less than the critical value. Numerical studies, I think, are still in their infancy, and I would bet that there's still a lot of great richness in this problem that remains to be uncovered. So I now want to turn to geometrodynamics in colliding black holes. This is a diagram that was drawn for me by an artist based on my own sketch when we were beginning to talk about LIGO in the mid-1980s, when we just built the collaboration between Caltech and MIT. And this was my imagination of an embedding diagram when two black holes went around each other, collided, merged, and produced gravitational waves. And we already knew from order of magnitude analyses that the power output in gravitational waves would be somewhat larger than the luminosity of all the stars in the universe put together. Only when we had the numerical simulations could we say that this is a factor of 50, say, for the first merger that LIGO saw. And we knew that if there would be no electromagnetic waves emitted whatsoever if there was no matter in the vicinity. But if there is a disk of matter in the vicinity, particularly a magnetized disk, you might get some electromagnetic waves from the merger disturbing the disk. And so that's what's being searched for. But the key thing is that throwing away, ignoring the possibility of a disk of matter in the vicinity, this is something that produces only gravitational waves, not electromagnetic waves. The important thing to me when we began thinking about this was that the details of the collision, the geometrodynamics, would be encoded in the gravitational waves waveform. And so in the early 1980s, when I and others began to believe, based on astrophysical arguments, that the first thing LIGO would see would be colliding black holes, which is what was the first thing, I just wrote down a hypothetical waveform that looks like that and said, gee, we might get something like this. There will be an in-spiral where an oscillatory in-spiral where the waves oscillate to higher and higher frequencies. There will be a merger when it might be really very interesting due to nonlinear dynamics, and then there will be a ring down as the final black hole rings in normal modes of oscillation, ringing like a bell. And so the challenge was to do the numerical simulations for the merger phase and see what we got. I'm going to now show you an example of a numerical simulation, which I also showed in my public lecture yesterday. It's the simulation that the SXS collaboration did of the first gravitational wave that LIGO saw, what's called GW 150914, because it was seen on September 14th, 2015. And this is the simulation by the SXS collaboration. It was actually Caltech, Cornell, Canadian Institute for Theoretical Astrophysics at that time, Cal State Fullerton, Oberlin, Washington State University. And the people, the leaders of the effort, people who wrote the code, the so-called SPEC code, the spectral Einstein code, because it's based on pseudospectral computational methods. Larry Kidder, Cornell with Saul Pfeiffer, came to Caltech and then to CETA and is now at the Albert Einstein Institute in Germany. And Mark Shield came to Caltech and stayed. And so, what I depict initially is the space-time metric in the orbital plane, as I did yesterday, but now I have to make a confession for the physicists and mathematicians that I claim this is what it would look like as seen from a higher dimension, and that is not quite true. The central issue is that if you have a two-dimensional surface that is curved, you know it can always be embedded in a flat higher dimensional space, in a flat three-dimensional space. And so it's a natural thing to try to draw it, the orbital plane of the two black holes, as embedded in that is the spatial metric, the two-dimensional metric of that orbital plane, as embedded in a three-dimensional Euclidean space. You're not guaranteed that the space will be Euclidean. It could be Minkowskian, so that's another issue. But you do have the problem that although you can do the embedding locally, you cannot do it globally. So you go around this black hole and you come back, and you will not come back and join on smoothly to where you were. And so we abandoned rather quickly trying to do this in the fully honest way, because this diagram would have glitches in it because of the global structure not being capable of being embedded in a three-dimensional space. So instead, and this was Harold Pfeiffer who had the idea to do this and made this movie, what is done is to plot vertically minus the sign of the scalar curvature of the metric of that orbital plane, that orbital surface, divided by the square root of the scalar curvature. So you're plotting something that has dimensions of length upward, and then dimensions of length horizontally. And the diagram looks much like what you would get from an attempt to do an embedding diagram, and this is what's actually plotted. So this really does truly exhibit the space-time geometry, but in a more complicated way than I would say in a public lecture.
What you're drawing actually, though, is the maximal hypersurface. You have a family of maximal hypersurface. So choose the time slices.
So you're doing a numerical simulation, and the computer code chooses the time slices in a way that basically avoids singularities and as effectively as it can. And so, roughly speaking, you have a spatial grid that is as nearly Euclidean as is possible in the presence of the space-time curvature. That's very roughly speaking. The SXS code uses a different coordinate system than other codes, but everybody's codes is doing all they can to avoid singularities. And so the diagrams would be a little different with somebody else's code, but they are should be more or less pretty much the same. So it's not a maximal hypersurface. It's the time slices that the automated computer code happens to have chosen after the numerical relativists have worked very hard to get an algorithm for the choice of time slices that avoids singularities. So there is a significant amount of arbitrariness in here. You should regard this as qualitatively meaningful, but not really quantitatively meaningful. The color coding is the so-called lapse function, if you know the 3+1 split of the space-time metric. And the arrows are the negative of the shift function. So roughly speaking, the color coding is the slowing of time, and the arrows are the dragging of space into motion, very roughly speaking. But the shape depicts then the two-dimensional metric of the slices of constant time. The color, the lapse function, and that is the time, roughly speaking, the time part of the metric, the contravariant time part of the metric, and the arrow is the shift function. And as I showed last night, what you get putting this into slow motion as it nears the singularity is a very interesting wild splash like you see in a storm at sea, the surface of the ocean. And then an oscillation with gravitational waves going out. So these finally had them, and they produced waveforms that agree beautifully with the gravitational wave observations, but they miss most of the dynamics of curved space-time, as I remarked last night, and I want to now elucidate in a little more detail. And so recognizing that this was missing a large fraction of what was going on, together with some former graduate students and postdocs, not of myself, but of Yanbei Chen, who was my successor in leading the research group that I used to lead. In 2009, I retired and turned the research group over to Yanbei, and we did this work in 2011, and these people were all students or postdocs of his. And I had the joy of retiring so that I could collaborate with brilliant young people without having any responsibility whatsoever for their careers or for mentoring them. And this is a joyful way to do science. And it's Yanbei's job to mentor them. And so the basic idea of what we did in order to was we wanted to visualize the Riemann curvature tensor. And I remind you that in special relativity, the electric and magnetic fields depend on the reference frame you choose. And when you make a boost from one reference frame to another, they transform among themselves, the electric field and magnetic field, and it's kind of a complicated sort of a way. In curved space-time, the analog is you choose some sort of a time slice of constant time, which the computer is generating, as I said before. Then having done that, this 3+1 split of space-time into space along this time slice and time orthogonal to it, that makes a split of the electromagnetic field tensor into the electric field and the magnetic field, which are fields that reside then in this slice of constant time. And we visualize those fields with magnetic field lines and electric field lines, such as the dipole magnetic field around the Earth. So this is all very familiar. In a similar manner, if you take the Weyl curvature tensor, or for my purposes, I'm working in vacuum, and so the Weyl curvature tensor is the same thing as the Riemann tensor in vacuum. So I'm just talking about the Riemann tensor in vacuum. When you do this 3+1 split of space-time into space plus time, the Riemann vacuum Riemann tensor breaks into two parts, which are symmetric, trace-free tensors in 3 dimensions that live in these space slices. These are often called the electric part and the magnetic part of the Weyl tensor or of the vacuum Riemann tensor. In a local orthonormal frame, we can think of with time going orthogonal to these space slices and space lying in the space slices. The electric part is the time-space part of the Weyl tensor. The magnetic part is the dual of the space-time part of the Weyl tensor. That's the Levi-Civita tensor. Now, it turns out that physically, the electric part is actually the tidal field. It describes tidal accelerations. In Newtonian theory, it's the double gradient of the Newtonian potential, or the first gradient of the gravitational acceleration. So if you have two particles separated by a separation vector, c, a spatial separation vector, the acceleration of this particle relative to that particle, as appears, for example, in the equation of geodesic deviation, is just minus the tidal tensor contracted into the vectorial separation of the two particles. And so we don't use the phrase electric part of the Weyl tensor for E. We just call that the tidal field. It's the tidal field contracted into the vectorial separation. The other piece, the magnetic part of the Weyl tensor, describes differential frame dragging. So if I put a gyroscope at the location of this particle, and I have inertial gyroscopes at the location of that particle will see this gyroscope at the tip of C precess around and around relative to the inertial frames at Q with a angular velocity. I call it a delta omega because it vanishes in the limit as the separation vector vanishes. That is of the Weyl tensor with the separation vector. And so that this then BJK we call the frame drag field because in this sense it describes differential frame dragging. Now let's just talk about, as I did in my talk last night, placing my wife above the a fast spinning black hole now. If she's above the north pole of the fast spinning black hole, she will see a differential frame dragging that is counterclockwise, in the sense that the gyroscope at her head, relative to her inertial frames at her feet, goes around counterclockwise. And similarly, the gyroscope at her feet, relative to inertial frames at her head, goes around counterclockwise. And this, I'm sorry, I'm doing the stretch and squeeze first. Okay, so excuse me. So she's squeezed from head to foot at the North Pole, stretched from head to foot at the equator. Many people don't realize this, but for a fast-spinning curved black hole, you get a squeeze radially at the North Pole instead of a stretch. And so the relative acceleration of her head and feet divided by her height is the tendicity, and it's the normal component of the tidal field. Tendicity comes from the Latin tendere for to stretch. And in the equatorial regions, she is stretched, again with a tendicity that is the relative acceleration divided by her height. And so we think of ourselves as having a blue tendex, a region of large squeezing at the North Pole, a red tendex, a region of large stretching in the equatorial region. Then outside this black hole, if I put her at an arbitrary location, there are principal axes of stretch and squeeze, as I talked about before when I was talking about the tidal field's nearest singularity. And the integral curves of the eigenvectors of the tidal field go along those principal directions. And we talk of the tendicity as being an eigenvalue of this tidal field, and tendex lines as the integral curves of the tidal field. And since this is a 3x3 matrix, or a symmetric second-rank tensor in 3 spatial dimensions, through every point there are actually 3 tendex lines go through every point. And you have red tendex lines, stretching tendex lines that come out of the equatorial regions. You have blue squeezing tendex lines that come out of the pole, swing around, go back into the pole. And then you have blue Tendex lines that come out of the black hole and spiral around and around, going off to infinity. That's 3 families of Tendex lines, with 3 Tendex lines going through every point. So it's a little more complicated than electromagnetism, but these are the analogs of the electric field. And we refer to a Tendex as a collection of Tendex lines with large tendicity, large stretch or squeeze. And so you have a fan-shaped Tendex coming out of the equatorial region of a fast-spinning black hole. And you have a toroidal surface that's actually symmetric Tendex coming out of the North Pole and going back into the South Pole. Then going back to what I started talking about, the differential frame dragging, similarly, you have a horizon vorticity, which is the normal component of the frame drag field. It's the angular velocity of the relative angular velocity of the inertial frames at her head and at her feet divided by her height. And so you have this counterclockwise vorticity in the northern regions. So I paint the northern part of this black hole red, and clockwise vorticity in the southern regions. She's twisted, her inertial frames are differentially twisted clockwise. And again, the normal BNN is the normal component of this frame drag field. Then outside of the black hole, you have these vortex lines, which are along the principal directions of the differential frame dragging. So a vortex line is an integral curve of an eigenvector of the frame drag field. And the vorticity is an eigenvalue of the frame. You can think of these vortex lines, as I said last night, as guiding a whirling, a twisting vortex, a vortex of twisting space, or the guiding centers for a vortex of twisting space. So this is the pattern outside a curved black hole. The clockwise vortex lines come out of the south polar region. They go around. She's twisted along that principal axis. They go around and come back into the south polar regions. And the counterclockwise vortex lines come out of the north polar regions, go around and back into the north polar regions. And there is hardly any twisting at all in the equatorial regions. So this is the depiction now, the full depiction of the Riemann tensor of a curved black hole. This pattern here of vortex lines and the pattern I showed you before of wherever it was, the pattern of Tendex lines. So you have the pattern of vortex lines, the pattern of Tendex lines, give you the full description of the Riemann tensor visually for a fast-spinning black hole. A region where the vorticity is large we call a vortex then. So you have a counterclockwise vortex sticking out of the north polar regions, a clockwise vortex out of the south polar regions. Then I showed last night what you get from a computer simulation if you have these vortices oppositely oriented on 2 identical colliding black holes. So a counterclockwise vortex up on this hole, clockwise down, clockwise up here, and counterclockwise down. And as I showed last night, the 2 black holes collide. You form an event horizon that has 4 vortices on it. And those vortices retain their individuality robustly. And the full dynamical behavior is one of exchange of vorticity as the merged black hole oscillates. What was originally clockwise is now counterclockwise, is now clockwise, is now counterclockwise. And as I described last night, what happens is that once the black holes have merged, the actual clockwise vortex emerges from the north polar regions, goes back into the south polar regions. There's been a restructuring, a reconnection of the vortex lines, analogous to magnetic field reconnection. And the counterclockwise vortex comes out of north polar regions, go back into the south polar regions in this black hole that now has 4 vortices on it. And every time the oscillating black hole goes green, the vortex lines have popped off of the oscillating black hole. The clockwise and counterclockwise ones embrace each other, form a torus, and these tori, one after another, go traveling outward from the black hole. into interstellar space. The Bianchi identities, which you recall are identities that the Riemann curvature tensor satisfies, if you go into a local Lorentz frame, they take a remarkably simple form that looks just like dynamical Maxwell's equations. The time derivative of the tidal field is the curl of the frame drag field symmetrized. The time derivative of the frame drag field is minus the curl of the tidal field symmetrized. It's really quite, this has of course been known for a long time, but this is the 3+1 split of the Bianchi identities. And what this tells you then, as you would expect based on the electromagnetic experience, is that as these vortices go traveling outward, their motion induces the formation of tendices or tendex lines with, for example, a stretching tendex lines going around this torus in that direction, squeezing tendex lines around the torus in the small direction. And these are gravitational waves. Gravitational waves consist of tendex lines and vortex lines, counterclockwise vortex lines, clockwise vortex lines, stretching tendex lines and squeezing tendex lines, a pattern of that sort. We have the technology to see the influence of the tendex lines in LIGO, but not the vortex lines. Measuring angular positions is a lot harder. If you have an orbiting collision, the generic case, it's rather different. I showed you the head-on collision because that's really quite cute. But if you have it's a little simpler behavior. If you have an orbiting collision, the merged black hole now is turning, tumbling over and over again from an orbiting collision. And the vortex lines reach out from this merged black hole and swing around in a spiral pattern. Clockwise vortex lines, counterclockwise vortex lines, but again their motion generates tendex lines that wrap around them. And so you have then gravitational waves that are generated by vortex lines that are attached to the merged black hole. But you have a different kind of gravitational waves generated by tendex lines that are attached to the merged black hole. You have stretching tendex lines right after the merger that stick out from the ends of this dumbbell-shaped event horizon. You have a fan-shaped squeezing tendex line sticking out of the equator. And as the black hole tumbles, the merged black hole tumbles, the tendex lines stick out, making a spiral pattern, and their motion generates entwining vortex lines. So you have two types of gravitational waves in general relativity, those generated by tendices that are attached to the black hole, those generated by vortices that are attached to the black hole. And it turns out that the normal modes at late times of vortex-generated waves, they have one parity. Those that are tendex-generated waves have the opposite parity, but the patterns are almost identical. And this has a very important consequence that you can have then vortex-generated waves and tendex-generated waves the same pattern, but opposite polarity or opposite parity. And so they will superpose constructively in one direction, say in the north polar direction, and destructively in the south polar direction. So you could have a huge amount of momentum going off in gravitational waves in the north polar direction and very little in the south polar direction. And that will give the merged black hole a big kick, and it can go flying off at thousands of kilometers per second due to this huge kick that arises from the near duality between the two types of waves. The remarks about gravitational wave observation should be obvious. LIGO's made its seeing gravitational waves. In the numerical simulations, we compute the waveforms, and we also see the nonlinear dynamics. And the waveforms agree with the observations of very high precision. We've seen so far 6 emerging black holes. In each case, there's beautiful agreement between the simulated waveforms and the observed waveforms. and you can go back to the simulations and see what was the geometrodynamics of that particular merging black hole event. An excellent agreement, as I say, between the observed and simulated waveforms. Well, my final remark, that I speculated in 1984 that the merger waveforms would be quite interesting. You go back to these waveforms, they're not very interesting at all. So why was I so wrong? I was very disappointed, I have to confess. I was very disappointed. And the answer is that the disturbances, when two black holes merge, depart very quickly. The black holes don't have the power to hang on to disturbances long enough for there to be strong self-coupling of the perturbations. Unless, and this is a very interesting, fairly recent work by Huan Yang, Aaron Zimmerman, Louis Lehner at the Perimeter Institute and at CETA and University of Waterloo, in which they point out, and they do perturbation analyses, and I think they also do some computer simulations. I've forgotten whether they've done it at the time of this paper or not. But if the final black hole is spinning rapidly, in the embedding diagram it has a long, thin neck. And so it turns out there are normal modes of oscillation that live for a long time trapped in this neck and only slowly escape. And they're held long enough that they can couple nonlinearly, and you can get a cascade. But it turns out in this case, you get a cascading of energy from small length scales to large, which is the opposite of what you get in three-dimensional turbulence, where the cascading is from large length scales to small. This presumably had to do with the axial symmetry of the neck in which these perturbations live, but I don't know that for sure. That's just a guess. And these are like two-dimensional turbulence. If you do a mathematical analysis in 2 dimensions of two-dimensional turbulence on a computer, you get this cascading from small length scales to large instead of large length scales to small. And so we have the hope that one out of 100 or 1 out of 1,000 of black hole mergers may produce a final black hole that's spinning fast enough that we'll be able to see very interesting final waveforms that display this two-dimensional turbulence. And so this is all I know at this point about geometrodynamics, near singularities, imploding waves, colliding black holes, and gravitational wave observations. But I do think if I were just starting my career and I were interested in nonlinear dynamics, and I also had some interest in computer simulations with codes that are now pretty mature, so you don't have to go in and invent the whole business. This is something that I would be quite interested in pursuing. But I'm in a different phase of my career, and so all I can do is do what John Wheeler did in exhorting me as a graduate student to study geometrodynamics. I just pass that message on to the graduate students that are here. Thanks.
Any questions?
So does observation support the existence of singularity, or it's still hypothetical and theoretical? And if singularity does not exist, do we still need dynamics?
So let me begin with the issue of dynamics. The nonlinear dynamics that we see, say, in colliding black holes, is not influenced at all by singularities. The singularities, if they exist, and we think they do, are inside a horizon and have no causal influence on this nonlinear dynamics. So the geometrodynamics is a generic, interesting process that is not directly related to singularities. In the first example I gave you, we're exploring what the geometrodynamics looks like as you approach a generic singularity. But that's just one venue for geometrodynamics, and it's not one where we have observational data. Here we are beginning to have observational data with the singularities hidden away. Is there observational evidence for singularities? Not direct observational evidence, but the beauty of the work that Roger Penrose and Stephen Hawking and Robert Garroch did in the 1960s and 70s is that it tells you that you can look out in the universe and you can see in the universe initial conditions or current conditions, which, say in the case of forming black holes, will lead, so long as you have a suitable positive energy condition, will lead to the formation of singularities in the future, at which point general relativity has to fail, and you have to presumably use laws of quantum gravity to analyze them. Or on a cosmological scale, looking back toward the beginning of the universe, as it was Hawking who really pushed this, applying the techniques to that. You see in conditions today of the expansion of the universe, with sufficient observation of the expansion of the universe, that independent of any symmetries going back toward the beginning, if there was a positive energy condition satisfied, there had to have been a singularity governed by the laws of quantum gravity at the beginning. So we don't see the direct evidence of the singularities, but we see the conditions that say there should have been a singularity at the beginning, and there should be singularities inside black holes.
I would be interested in your response to this question. How important was it to have the explicit Kerr solution for this LIGO gravitational wave? In other words, have there not been that explicit Kerr solution, would it have really changed the game?
I think it would have changed the game in the sense that you needed initial data. And the initial data were two Kerr black holes going around each other. And so I suppose you could have built initial data that you hoped were resembling something that might exist in the universe. But having the Kerr solution and having the observational evidence that suggests there really are Kerr black holes out there, not absolutely firm, but quite strong observational evidence, you had in your hands the foundation for building initial data for the simulations.
So you mentioned your disappointment in not seeing terribly interesting dynamics during the collision of two low-spin black holes, but is there room for interesting wave signals coming from mergers involving one neutron star or two neutron stars?
Yes, but the interesting waves are going to be strongly influenced by the shocks that form in this colliding nuclear matter, by the behavior, the nasty, dirty behavior of matter. The beauty of black holes is it's very clean. It's not mucked up by matter. And matter is really so complicated, and vacuum gravity is so beautifully simple, at least conceptually, that there also is the difference then that with neutron stars you don't know for sure the equation of state. You don't have it in hand yet the tools to do a really good job on the radiative transfer for the neutrinos particularly. It's going to be important for the dynamics. And so it's much harder to do realistic simulations. But on the other hand, from the observed gravitational waves, you get data that will help you pin down the physics that you don't fully understand. So it's a very different ball game when you're working with the neutron stars. It's more like conventional astrophysics, where you're having to go back and forth between the observations and the theory to try to get the physics of what the matter is doing straight from the observations. And yeah, the waveforms will be more interesting. They'll bring us interesting information about how the matter's behaving.
So the collisions that one is seeing now, the black holes are presumably essentially electromagnetically neutral, no electric charge, but in principle it might seem like an interesting problem to numerically simulate the collision of charged black holes. Has that been done? And
I don't know what work has been done on that. I should know. It's a shame that I don't know, but I haven't kept up with all the simulations people had done. When I was last looking closely, which is a few years ago, there had not been anything done really on this, and I don't know since then.
Might be interesting in particular.
Yes. We get what we believe are realistic limits just based on the behavior of plasma in the presence of very large charges. The plasma will quickly neutralize very large charge concentrations. And that's why we believe that in an astrophysical situation, you don't have strong enough charge on any black holes that the electric field will significantly influence the space-time geometry. Nevertheless, the electromagnetic fields have enormous impact on the matter, on the astrophysics. The jets that stick out of galactic nuclei, some of them presumably are generated by magnetic fields that thread through the spinning black holes and are held on by a highly electrically conducting accretion disk. And so you get really interesting dynamics in the matter, but not strong enough fields to affect to modify the Kerr geometry in a measurable sort of a way.
When you use when you look at critical phenomena, just a technical question. Is this a simulation that uses Wilson's renormalization techniques, or how do they go about that?
So these, in the critical phenomena you see here, are not in many body systems at all. The critical phenomena you see here are entirely in the dynamics of curved space-time. And so although you see the critical exponents you see in condensed matter critical phenomena, the mathematical techniques are completely different because you're seeing it in a system that is made of pure empty curved space-time instead of being made of a huge number of spins, for example. So, yeah.
Right, I see. Thank you. One other question. Do you care to comment on your opinion of the status of quantum gravity?
My comment is that I have no wisdom about this. I have an opinion, but it's not a very educated opinion.
Well, it's the opinion I'm asking for.
First, let me explain why I'm uneducated. We all have personalities, and my personality is that I much prefer to do research in an area where there's lots of elbow room. And there's too many people who are a lot smarter than I am working on quantum gravity, and there have been through my whole career, so I've stayed away from it. So that's why I'm not very well educated. I do have to say that I'm impressed, looking in from the outside, by the progress that I believe has been made with string theory and then moving on into M theory. And I'm hopeful that approach is going to really lead to a deep understanding. But I am very far from the subject for just the reason I described. So my opinion, and I have been wrong so many times before in my career, such as my total skepticism that you could have an acceleration of the universe. I had to see data from 3 completely different kinds of astrophysical directions before I believed that. So I've been so wrong before that you shouldn't take what I say at all seriously.
Okay, let us thank Kip for wonderful lectures again. Thank you.
Okay, thanks.
I have to go to the airport as well.